channel, and today we'll see how we can scale a NoSQL DB. Okay, before starting this video, I'll want to tell you that if you haven't seen my previous videos where I have explained how to scale a SQL DB and what is a tap theorem, you must go and see that before watching this video. You will have better understanding and better context when we proceed in this video. Okay. So let's get started. Why do we needed a SQL DB when we had no SQL or vice versa? So in SQL DB, what we said that we are having high consistency over high availability. Okay, so in CAP theorem, as we know, we have discussed, we have to decide between one of them, consistency and availability. So in SQL, we said we want consistency at as it is used for highly systems where data need to be consistent, like banking servers. Okay, so yeah, but there can be systems where we say we don't need consistency, just we need that the system should be up all the time, and if data is not that consistent, then also it will work, but system should not go down. Okay, in that cases we use NoSQL DB. So let's see how NoSQL DB actually manages this. Okay. So this is a basic architecture where you have a server and you have a database where from the server the read and write request comes in the databases. But what actually happens inside this? Let's see. Okay, so so achieve high availability. What in NoSQL database we do is we do data partitioning and data replication. Okay, this is the most common practice for achieving high availability. So what I mean by this is, so we have one load balancer, and where we will be doing a partition on based on some key. So let's say after partitioning, we get to know that we have to write in server DB server A. Okay, so when the request will come to write in server A, it will make sure that it is also replicating the same data as in any other server. For now, I'm saying that our replication factor is 1, so I mean 2. So we'll write in A in this DB as well as one more DB. So let's make it as clockwise. So when a write request comes at A, it goes to B also. Similarly, if a write request comes as at B, it goes to C, and if it comes as C, it goes to C and D, and similarly for D, it goes to D and A. Okay, so achieve higher availability, we'll say that our replication factors much more. We can add that. We can increase our replication factor. So let's suppose when we write request comes at A, we'll say that I write at A, B, and C. Two extra writes I'm doing here. Okay. So similarly for B, C, D also. Now if we see that this is okay, but you'll say that what about the make replication factor to n? N means number of database servers which are there, but it will slow down your writes. Okay, so because you will be ensuring that the writes are happening in replication servers also, so that will slow down. And also it will increase your cost as you are saving extra data. So yeah, it will be very much highly available, but you will be having lot of cost in that way, and also the latency will be very high for writes. So what else we can do is we can say, like, if we are writing 3 servers and if we get requests of 2 servers also that it is written, we'll say it's okay. Like I'm writing at A and it is replicating to B and C. If I say that my write has happened to B, I am okay with it. I will tell the user that your write is done, and in the background, C the write at C will happen. If it is happened, or it is an error, I don't care. I am sure that there is some kind of replication or happened, if or not all. Okay, like this, you can do your writes. But what about reads? How to know that which server you have to read and where to get data from? So for in these kind of cases, what we do is we one make, let's suppose this is our document, NoSQL document where we have booking ID, amount, date, and user ID which has done that booking. Okay, so what I'll say that let's suppose we do partitioning key as user ID. So whenever there is write coming, so the load balancer will pick this user ID value and it will see it at which partition I will have to write. Similarly, when we are doing a read, so obviously we'll do a filter, apply a filter. So if you want to get faster reads, it is said that you should apply user ID in the filter because it is a partition key because database will know at which partition server it has to search for that particular record. Okay, otherwise if you don't give user ID in a filter clause, it will search in all the servers parallelly and combine that result and give back to you, which is going to take much more time and lost lot of infra also. So that is not recommended. Always make sure that your partition key such that your all the query patterns has that partition key. And for more faster reads, what you can do is you can create indexes on, let's suppose, user ID and date. Okay, or maybe on booking ID. So if I'm having filters where I'm searching for booking ID of a particular user, I will have filter on booking ID. I will have index on booking ID and filter and partition at user ID. Similarly, for date also, we can make any key as partition or index key based on our query patterns which we want. We have to figure out what amount of queries and which queries will be doing most. According to that, we can do these type of we choose these type of any kind of a partition key and index key, whichever suits our use case best. Okay, so that's all for optimizing reads. Now you'll say that since we are writing at many servers, what in case of for in case where any of the servers down, what will happen? Failure cases. In reads, if server A is down, we'll go to B because the replication of A was set to B, and these all information are there in um, load balancer. That if A is down, we'll go to B because replication was done at B also. So in reads, it is fine. But what about writes? Let's see. So this load balance is connected to all the three servers A, B, and C. Okay. Let's suppose we are writing, updating name to XYZ at A. So it is replicated to B also and C also. But what if A is down? Okay. A is down. So the write will come at B. And we have updated name to XYZX and it is replicated to C. Okay. So now what if A comes up? And if as soon as A comes up, I want to see and well and a read query comes. What is my name? So filter on a name, so it will return this value, and it will also check for this replication that hey, you have the same value or not. So B will tell no, I don't have the same value, and C will also tell no, I don't have the same value. Okay. So what will happen? It will store like this. This name was updated by server A. It was updated by server B. It was updated by, sorry, this was updated by A. This was updated by B. Okay, so this was updated by A and it was updated by B. So it will save something like this. And when a read query comes now at this point of time, when this has happened and A has come up again on a read query comes, it will fetch like I have this record, but B has this record, and C also has this record. So since B and C have same number of records, so it will take one. Let's suppose we are taking B. Now we have updated name XYZ in A. We have this XYZ at A. So it will know like this is common, so we'll neglect that. It will be cancelled out. Now the value of name is XYZX at B. So the updated value must be this. So it will return this and it will update on A also that this was the value when I was gone. Okay. So like this, it manages to have consistency, but there is a catch here. Okay, let's suppose um, when this ABC was written, the C was down. Okay, so it can be, sorry, XYZ, X was written by B, the C was down, it was not able to replicate here. Now, a third request comes, which when C was up, but B and A was down. So we'll say that it was updated by C. Okay. So as soon as this is done, and when a read request comes again at A, and now all the servers are up. So what it will return? Okay, so it will return this. B will say these are all the versions which I have, and C will say, hey, this is all the versions which I have. Okay, so this XYZ is common in all, so it will be cut down. It is gone. Now there is a conflict between XYZB and XYZXB and XYZYC. Okay, so now there is a conflict here. So what A will do is we can have multiple mechanism like um, we can send one of the ways we can send any of the requests to the user, and it's if it is not correct, user will eventually update it. Otherwise, we'll send both the values to user and say that, hey, choose one. We have a conflict here. We could not able to update due to failure reasons. So user will give you select the correct value, and it will be eventually updated in the database, and all will have the correct value. So this is what eventual consistency is. Eventually, uh, this data is getting consistent, but for some period of time there were conflicts. This is what we don't face in SQL DBs because they are consistent. They do right because we are not doing partitioning there. We are not doing replication. Partitioning can be done for achieving high availability there. Uh, but since so partitioning can only be done in SQL DB when you don't have that many relationships. Okay, so if you don't want to do relationship query, yes, you can partition like it's the same like NoSQL. Um, but it both has their pros and cons. Like in SQL, what we do is when we want to achieve high consistency, we want to update that particular value at both a reader, all the readers like that we work. Uh, but here, what we see, we do a replication level at particular point only. In SQL, the write is done at master only. So master is the source of truth. If you want to read, get the updated value, we can read from master. That will have always have consistent value. But this is we don't have that case here. Okay, because we are figuring out we want high availability here. And yeah, so whenever you want to design any system, you have to choose between availability and consistency. So you can decide based on your requirement. Yeah, that's it from this video. Do let me know if you want to watch any other video or any other topic you want me to create video on. I will be happy to do that. Till then, take care.